All right, this is the very last lesson in Unit 1. And we're going to talk briefly on logic that we're going to need throughout the unit. The first thing is a conditional statement. Another name for this type of statement is an if-then statement. You hear these throughout everyday life. For example, a store might say, if you are not completely satisfied, then your money will be refunded. There's two parts to these type of statements. The first one is your hypothesis, and that's whatever is right after the word if. So this would be your hypothesis. The second part is your conclusion, and that's whatever is after the word then. So the only way your money is going to be refunded here is if you tell them you are not completely satisfied. So in the next example, if a rectangle has a width of 5 feet and a height of 4 feet, then its area is 30 square feet. Your hypothesis is that the rectangle has a width of 5 and a height of 4. Your conclusion then is that the area is 30 square feet. With conditional statements, we have truth values. So that means, is the entire statement true or is the entire statement false? A conditional statement is only false when your hypothesis is true and the conclusion is false. So we have to start with something that's true. Okay, if we can't say a statement is false unless there exists a situation that could be true. Okay, so even if your hypothesis is completely weird, it just doesn't make sense, the statement will still be true because we have to start with something that's true and then prove that it's false. So if you look back to the example that we were looking at, rectangle has a width of 5 feet and a height of 4 feet. That can be true, there's nothing wrong with that. But would its area be 30 square feet? Remember, area of a rectangle, length times width. No, that is false. So then your entire statement, okay, the entire statement then is false. So it's only when your hypothesis is true and your conclusion is false. Let's look at a truth table to show this. A truth table is just a picture representation of all the possible outcomes. Usually, for whatever reason, we use the letters P and Q. P is your hypothesis, Q is your conclusion, but that's not always the case. Okay, your symbol here is just this arrow, so you can see the arrow, and that's read as if P, meaning if whatever P is if that, then we know Q. Okay, then we know our conclusion. Let's look at this truth table here. If your hypothesis is true and your conclusion is true, then we know our whole entire statement will be true. So if we had said, if a rectangle is a width of 5 and a height of 4, then the area is 20 square feet. Yep, no problem, that's true. The second one's what we just talked about, though. If your hypothesis, so this is your hypothesis and your conclusion, if your hypothesis is true and your conclusion is false, then we know this entire statement is false. And the last two are still true, okay? Again, we can't prove something's false unless the hypothesis can even exist. Okay, so that's the weird one. The thing to remember here, though, is this column right here. All right, so write as a conditional. A square has 4 sides. We need it if a shape is a square. Then, so that would be our hypothesis, then it has 4 sides. Okay? Is this true or false? If a shape is a square, well, we can have a square for a shape, so that's true. So we're looking at one of these two. Then it has 4 sides. That's true. So this entire statement then would be true. All right, sometimes though, you'll see this symbol here, and that's the symbol for not. And we have 3 types of conditional statements we can write based on the original. So let's say our original here is if P then Q. Okay, our converse statement, these are 3 that you're going to have to memorize. You're just going to switch your hypothesis and the conclusion, excuse me. So it's if Q, then P. So you'll just switch whatever wording is there. The inverse tells you that you need to negate the hypothesis and conclusion, meaning you throw in the word not. So if you need to write that, you put in the word not. And again, we already said the symbol is that little squiggle. So if not P, then not Q. The last one, your contrapositive, you are going to switch your hypothesis and conclusion, and you negate them as well. So if not Q, then not P. All right, let's look at an actual example here with some words. If a shape has 3 sides, then it is a triangle. Your converse, we said that you simply switch it. So you're going to say if a shape is a triangle. So here we're putting our conclusion first. Then it has 3 sides. And then you put your hypothesis. So there we just switched it. Your inverse, you keep the same order, but you throw in that word not. So we're going to say if a shape does not have 3 sides, then a little bit smaller, it is not a triangle. Okay, so again, same order. The last one though, contrapositive, you switch and negate. So if a shape is not a triangle, and I'm just going to use this symbol here for space, then it does not have 3 sides. Okay, so you need to know converse, switch, inverse, negate, contrapositive, switch, and negate. Your biconditional statement is when the conditional and the converse are both true, so your original and your converse are true statements, and we join it using the words if and only if. The symbol for this one is just an arrow, is a line with arrows on both ends. So our example here is if 3 points are collinear, then they lie on the same line. The converse, if 3 points lie on the same line, then they are collinear. That is true. So your biconditional, would be 3 points are collinear. If and only if they lie on the same line. So if and only if they lie on the same line. So you could still use symbols as well, and we'll see that in practice in class. But then you'd have something like P, if and only if Q. All right, this concludes this lesson.